So, when we talk about computer architecture, we have the first basic thing that comes into a computer, which is the CPU. You might have heard of this, and you might see like in normal desktop computers or PCs, there's this big box, and that is the central processing unit. So this is also known as the microprocessor or processor, is central to all modern computers, including tablets and smartphones. So a microprocessor and a processor is also present in your phones and computers and like laptops, everything, in smaller sizes and like lesser area covered. But the most obvious or the biggest one you'd see is the ones that are connected to PCs or like desktop computers. And CPU is very often installed as an integrated circuit on a single microchip. CPU has a responsibility for the execution of processing of all instructions and data in a computer application. So the three things that a CPU has is a control unit, an arithmetical logical unit, and registers and buses. So a control unit we're going to be talking about in detail as well. The control unit is basically where all the processes are controlled from, where all the calculations are being told of when to go where and how to store what, basically. And an ALU, an arithmetic logic unit, is where all the calculations take place. And all the logic, the topic we did first, remember logic gates, that logic unit also uses that as well. And the last thing would be registers and buses. Registers are basically a very small memory space where you use these in calculation. So whenever you're having some calculation in the ALU, which is the arithmetic logic unit, you want to store some of the data temporarily, you'd use registers for that. And the way that the data moves across a computer in different units is through buses. We're going to be talking about this in detail as well. Do you have any questions so far? Okay. So the main architecture that we commonly understand for computers is called the von Neumann architecture. This is by a scientist called von Neumann. He named it after himself. And in like the earlier times, computers were fed data while the machines were actually running. It wasn't possible to store programs or data, which meant they couldn't operate without a person. And because this was very inefficient, there wasn't any proper interface, there was no proper working except for a computer couldn't function on its own without a person. And so it was becoming very harder to deal with. And then this von Neumann guy made up basically an architecture for the computers to make it function better, and an automatic characteristic would come into it too. So here, the concept of central processing unit, the CPU was able to access the memory directly. That is the new change that the von Neumann architecture brought in. And computer memories could store programs as well as the data. So instead of just being able to store data and maybe do a few calculations, it would now be able to store the data in its memory and directly access it whenever the person wanted to access it. And stored programs were made up of instructions which could be executed in sequential order. So a sequential order is basically if they're saying the instructions were executed in some kind of sequence, some kind of pattern, and that would be easier for the person to understand what is going on, as well as the computer to we'd be able to spot errors in it a lot easier. Right. So let me zoom in this as well. So this whole image you see here, this is the von Neumann architecture. We're gonna look at this in a little more detail. So pay attention to the green rectangles here. This is all of the units that they're talking about. So the control unit mentioned here, and below this is connected both ways to the arithmetical logic unit, the second part of the CPU or the computer architecture. And you can see another green box here called the system clock. So the system clock is basically it's basically something that we use to time any task performance. So the same way we have time as a quantity to understand how much time has been passed. For example, this class is going to be 1 hour long, and I'm going to be covering this subtopic, and another subtopic, right? Similarly, when a computer does some kind of process, for example, I wanted to open an application, it has a system clock on it as well, timing how long it takes to perform a certain task. And without the system clock, everything might like we would never be able to understand how much time it's taking. And if we don't know how much time it's taking, it'd be harder to reduce the time taken and so on.
Okay.
Sorry?
All right.
Okay, so the orange boxes you see here, let's look at these. Um, a lot of these are the registers. The registers, as I mentioned before, are very small memory space, like memory storage space. And like, okay, so a memory address register is as the name suggests, a register to store all the memory addresses. And then there's also a memory data register, meaning it stores all the data that's stored inside that address. So as we have, let's say we have, for every person, an address exists, right? Like there's this person here. This person would have, like, let's say this person's Bob, has some home address on his ID card to represent where exactly he's being stored or where he's living, right? Similarly, when it comes to data, when it comes to any piece of data, you need to know where this piece of information is being stored. And like that's how you'd access it in main memory as well, right?
Okay.
Okay, so the next thing we have here is the current instruction register. This register stores what current instruction is being processed. As the name suggests, it's just telling you that whatever process taking place currently, it's storing that address space. And then we have the accumulator. The accumulator you can see is linked directly to the arithmetical logic unit. This means this also, you can understand by this itself that this accumulator stores the results of what's being, accumulator is a type of register. So it's storing all the calculation results taking place in the ALU itself.
Okay.
Right? And then there's one more left, the program counter. The program counter is there another register which represents that like how many programs or how many tasks have been executed for a certain amount of time. Right? Now, I'd like you to see the lines, the arrows that are going around here. It might look a little complicated, but what I'd like you to notice is that basically these lines are representing the buses. As I mentioned before, buses are the method through which any amount of data or address or anything is transferring from one unit, from one register or unit to another. So that is what's going on here. You can see this area here says address bus, and here it says data bus. Here it says control bus. Now you'd notice one thing is that the control bus has an arrow going outward and an arrow going inward. And as the control bus says, we're going to look at this in a little more detail a little later as well, that the control bus is responsible for transferring all the data that is meant to control the the inputs and outputs of a computer architecture, not just the inputs and outputs, or just how the data flows through a computer system.
Okay.
All right, and so there's an address bus. You can see this is also connected to the MAR, memory address register, and it's only in one side. It can only go this way, meaning it's basically a unidirectional bus, which can only transfer addresses to places, but not back from places. And this address bus is like, again, it's related to the memory address register to transfer all the addresses from one place to another. And then there's a data bus, which transfers all the data stored inside a specific address from one place to another, and it's bidirectional because it's going outward and inward. All right? Okay, do you have any question in this architecture?
Wait, can I look at it for some time?
Yeah, sure. Are you done?
Yes.
Okay. So, right. So these units that we discussed before, we'll look at these in a little more detail. You can make like actual like proper notes about these a little later too, just to see the formal definition of it. So here it is that the main components of the CPU are the control unit, ALU, and system clock. Now, the arithmetical and logic unit allows the required arithmetic like calculations such as add, minus, multiply, divide, shifting, or logics such as and, or, like the NOT, NAND gates, all of those operations to be carried out while a program is being run. And it is possible for a computer to have more than one ALU to carry out specific functions. So it's possible that you have more than one arithmetic logic unit to perform your calculations and logical implications. So multiplication and division are carried out by a sequence of addition, subtraction, left and right logical shift. So multiplication and division, it's not like directly access or directly possible through an arithmetic unit. There's another method to do that through the basic things that we have, like adding, minusing, and the shift right operations that you're studying in class right now too.
Yes.
Right? So let me go down from here. Okay. Control unit. Now, what is the control unit? It reads an instruction from memory. The main function of it is to read an instruction from memory, and then the address of the location where the instruction can be found is stored in the program counter. So the initial instruction is stored on the PC. This instruction is then interpreted or understood using the fetch-decode-execute cycle that we're going to look at a little later. And then during that process, signals are generated along the control bus, one of the buses that we talked about before, to tell the other components in the computer what to do. And the control unit ensures the synchronization of the data flow and program instructions throughout the computer. A system clock that we mentioned before as well is used to produce the timing signals on the control bus to ensure, let me just highlight this part. The system clock is using to produce the timing signals on the control bus to ensure the vital synchronization takes place. So do you know what synchronization means?
As like fetch all the files and then download something.
Sorry?
I think it's to fetch all the download and stuff.
Synchronization is not exactly that, but it's like to be in sync with something, to make sure that everything is happening in a specific in it like a specific given time frame, and it's in sync with the other processes taking place.
Okay.
Right? So, right, without the clock, the computer would simply crash. It would not be functioning properly at all. And the RAM holds all the data and programs needed to be accessed by the CPU. The RAM is often referred to as the immediate access store. And the CPU takes data and programs held in the backing store, for example, the hard disk drive, and puts them into the RAM temporarily. So because RAM is basically random access memory, right? And this memory is considered temporary memory, and so all the temporary memory being we don't need to be permanent is being stored in RAM. Therefore, the CPU takes data and it's storing all that in the backing store and then putting that into the RAM temporarily. That's why they've always associated RAM with temporary word. So this is done because read operations carried out using the RAM are considerably faster than read operations taking the operations to backing store. And consequently, any key data needed by an application will be stored temporarily in RAM to considerably speed up operations. So basically, there's a RAM and there's a ROM, right? RAM is random access memory, and then ROM is read-only memory. So the main difference between these two, and we're going to be studying this a little later too, is that RAM is temporary while ROM is permanent. ROM is something that can only be read into. You cannot delete things from there in like the most general kind of ROM. You cannot delete things from there, and that's why if we always store things in ROM automatically, it's going to make our system slower because we need to be able to delete and upgrade files as well, right?
Yeah.
Yeah, so that's why they mentioned this here is that They're storing it in RAM temporarily so that they can speed up the operations.
All right.
Okay, so the next thing we're gonna see again is registers that we saw before too. Is that all right? So registers are one of the most fundamental concepts of von Neumann system, and registers can be general or special purpose. The ones that we talked about in this diagram, the orange ones, these are all special purpose registers because they have a kind of functionality that it needs to perform. So here, we will only consider the special purpose registers. A full list of the registers used in the textbook are summarized here. So the first one that we had seen was the current instruction register, or the CIR. And the function of this register is that this register stores the current instruction being decoded and executed. The next one was accumulator, this is the short form for it. This register is used when carrying out the ALU calculations, the arithmetical logic unit calculations, and it stores data temporarily during the calculations inside this accumulator. And the next register we have is the memory address register, which stores the address of the memory locations currently being read from or written to. So either any data memory storage location, either that data is being read or it's being written to a certain area, right? So it stores the address of that memory.
Okay.
Right, and then there's a memory data register or memory buffer register. Data and like buffer, you could use either word, but normally the abbreviation you use is MDR, so it's better if you stick with that. And then this register stores data which has just been read from memory or data which is about to be written to memory. So whatever address you were looking at in the memory address register, you're going to be looking at data of that specific address. It's as simple as that. And then we have the program counter, or in short form PC. This register stores the address where the next instruction to be read can be found. So it's storing the next thing that we need to basically like know where the next instruction is going to be. So do you have any questions so far?
No.
Okay. Right. Have you done this in your classes yet?
Yes.
All right, okay, cool. So the next thing we're gonna see is the buses, like the buses that we said, the control bus, the address bus, and the data bus. This figure can show you how like the data flow is being considered. So you can see that the control bus is being pointed towards and inwards to like from and to literally everything, from the CPU to the CPU, from memory and to memory, and from the ports and to the ports, and the ports are automatically connected to the input and output devices. So the next one we had was the address bus, and now this one is always going to be unidirectional. You can see that it is the addresses are being sent from the CPU to the address bus, and then from the address bus to the ports, but never the other way around. Okay.
Yeah.
And then there's data bus, which is again it's also it's a bidirectional, so it's similar to the control bus. It's being sent to and from all of the units, the CPU and the memory and the input output devices.
Okay.
All right, so memory. The computer memory is made up of a number of partitions. Each partition consists of the address and its contents. Uses this table here, this at the left side, uses the 8 bits for each address and 8 bits for the content. So you can see at the left side are the addresses being stored, and the contents or the data is at the right side. And then in a real computer memory, the address and its contents are actually much larger than this. Of course, like when you look at actual data, it won't be as compressed and as small as this. It's gonna binary values normally they store a lot of data, so it's gonna be in larger binary numbers. And then the address will uniquely identify every location in the memory, and the contents will be the binary values stored in each location. Now, let us now consider two examples of how the MAR and MDR registers can be used when carrying out the read-write operations to and from memory. So MAR is obviously, like, again, it's a memory address register, meaning it's being linked directly to your addresses. And then MDR would be like linked to your contents column. And now first consider the read operation. So if you want to read something from memory, like you want to access it, then we will use the memory section shown in the table 3.2, this table here. suppose we want to read the contents of memory location, this memory location they mentioned here, quadruple 1 and then 0001. So let's look at this. Let's look for this exact memory location inside this table, which is this one, right? And they want us to read this data. Now, how is it going to read this data? It's going to look for this address, and the address of location this to be read from from is first written into the MAR. So this address is copied into the memory address register, the same thing in this register, and then right after that, you're going to a read signal is sent to the computer memory. So it's going to say that, you know, I want to read this certain data from this address. So it's going to look up the data stored in this memory address register. And that's why when this searches the data up in the table or in your database, the contents of memory location this is then put into the MDR, and then it accesses this data right next to it. And then that new data is being stored into the memory data register here.
Oh, okay.
Yeah, so like everything that was in the address, they're going to look for the data that's inside this address, which is the contents. So copy the contents to the MDR. And that's basically, yeah, and then that's basically your read operation done.
All right.
Okay, and now we have the write operation. So you want to write something to memory. And now let us consider, we're going to use the memory section shown in the table. Suppose the time we want to write, suppose this time we want to show how the value 10010101 was written into the memory location, this memory location. Let me highlight this. So we have this data, this is the data, and this is the memory location we want to write it to. I'll write it down here so it's not confusing. So this is the data, and this is the address. So they told you what data you want to write first. So you're going to store this data inside the MDR. So you can see this data is copied into your memory data register. And then once it's copied, you're going to look up this actually you're gonna want to store it to this address. Now you're gonna look up this address inside your table. It has it's on here, right? Let me highlight this. It's on here. And now that we have this, we have the address. We're just going to copy the contents of the MAR. We're going to copy the contents of the copy the contents of the MDR into the contents like block as well, which is right next to that, which is here. So once we do this, the write signal is sent to the computer memory, and the value of whatever we wanted to store will then be written into the correct memory location. Okay. Do you have any question?
No.
Okay. All right. So these are the descriptions, the descriptions of the system bus, address bus, and data bus. So the system bus here, it uses parallel transmission, which is covered in chapter 2. We're gonna look at that too a little bit, but basically parallel transmission means that it's simultaneously transferring data and from data and to data. So system buses is consisting of the 3 main buses that we talked about, which is the address bus, the control bus, and the data bus.
Okay.
Right, and each wire in the bus transmits 1 bit of data. There are 3 common buses used, which we said as well, address, data, and control. And then the address bus here, we've already discussed this. One point to note here, though, is that they mentioned the width of the bus. So it can tell you how much data is being transferred at one certain time. So the width of the bus, or how it depends on how wide the bus is. If the bus is very wide, or like the wire is very wide, that means more memory can be transferred to the location that we discussed before. So, and as we know that the address bus is unidirectional, right? So it can only transfer data one way. That means that it can transfer a certain address from one place to another in just to the other place. It can't go backwards. And here they have an example. A bus of width 16 bits can address 2 to the power of 16 which means 65,536 memory locations. So if they tell you the width of the bus, for example, here they told you 16 bits, you can tell them that basically with this width of a bus, you can access or you can transfer 2 to the power of 16 memory locations. Okay?
Oh,
So here, for example, sorry?
just okay.
Okay. So here, for example, they said the width of the bus is maybe 32 bits. That means 2 to the power of 32, which here they mentioned 4 billion plus memory locations to be simultaneously addressed. However, even this isn't large enough for modern computers. Normally, the computers that we use these days have an even bigger width of a bus.
Oh.
Right, and so the next bus we have here is the data bus, which is bidirectional, means it can transfer to and from places. And this means that data can be carried from the CPU to memory and vice versa, and from and to input devices. All right, and do they mention the width of the bus? Okay, so here they are talking about the width of the bus, and instead of seeing how many places are addressed, because obviously that was related to an address bus, that's why you would say it can address these many locations. But for a data bus, you'd be talking about the word length that can be transported. So the amount of data that can be transported and its keyword would be considered word length. So a word is a group of bits which can be regarded as a single unit. So for example, a 16-bit width of a data bus, or a 32-bit or 64-bit word lengths are the most common, and the larger word lengths can improve the computer's overall performance. So the larger your word length is, the more the more faster your computer system will be.
Okay.
Right. And then lastly, the control bus. So a control bus here, yeah, so the control bus is again, it's bidirectional, same as data bus. It can transfer data to and from places, and the control bus function is to carry signals from the control unit to all the other components and vice versa. And it is usually 8 bits wide. There is no real need for it to be any wider since it only carries control signals. So because a control bus's functionality is to tell the computer how to control the computer, basically. And for that, you don't need that much storage, or you don't need a really wide bus. You just need to transfer like very small like data amounts, which is just for the signals. That's why it's just 8 bits wide.
Okay.
All right. Do you have any questions so far?
Oh no.
Okay. All right, so the next thing we're going to be talking about is the fetch, decode, execute cycle. Now, this fetch, decode, execute cycle is basically a cycle that represents the process of how a computer works when any task is given to a computer. When you try to turn it on, if you try to maybe open Google Chrome, maybe if you try to close an application or watch a video, anything literally, or maybe you want to find some folders in your laptop already stored. Like all of this, whenever you try to do any of this, it doesn't just happen. It has a certain process it goes through to make it happen. And that is considered the fetch, decode, execute cycle. So just by these 3 words, fetch, decode, execute, what can you understand from this?
I mean, fetch is like maybe it's the files or any command
Yeah.
like you can is being fetched,
Mm-hmm.
and it's being fetched from part of the memory, which is the computer.
Yeah.
We could say like you can also say memory address, and it that memory address is stored in the MAR,
Yeah. Okay.
and the instruction which is being fetched that is stored in the MDR.
Exactly. And then?
and then what you're trying to say is that the parts, like the contents or the parts of the MDR is like basically copy the uh, CI.
Mm.
Yes?
Yes, exactly. So we're like everything that we discussed in the von Neumann architecture, we're making use of everything in that to make sure that this cycle works. And it's like fetch is exactly as you said, you're going to first like fetch itself, it means to get something, right? So in fetch, we're going to try to fetch the instruction first by the whatever the user wants to perform. So it fetches an instruction. And it doesn't just fetch the instruction itself, it fetches the address of that instruction so that we can store it in the MAR. And then the address of like is looked up, and then the data inside that address is put in the MDR, and then the MDR is copied. The data of the MDR is copied to the CIR so that we know like what current instruction is being processed. And then the PC is incremented by 1. So the program counter incremented by 1, so we can now know what the next instruction has to be processed. Now, once we have this current instruction that we want to process, which is in the CIR, by the way, so we're going to decode that data first. So when it comes to the decode section of the cycle, the instruction is decoded so that it can be interpreted in the next part of the cycle. And once it's decoded, it needs to be executed so that we can execute the actual process. We can finish it and then we can perform it and then execute it or remove it from the cycle itself. So the CPU passes the decoded instruction as a set of control signals to appropriate components within the computer system. Like it passes it to whichever part of the computer system it needs to be like sent to through the control bus. And then this allows each instruction to be carried out on its logical sequence. So whatever has to be performed, it performs that on the execution process, on the execution part of the process.
Okay.
Okay, and this cycle just repeats itself. It looks to see if there's any next instruction to be executed, or like in the PC, it sees if there's any next instruction, and then it just repeats itself.